magnetism part. So the techniques that were developed in this last section are absolutely critical to you being able to do well in the rest of the semester. So that means that you make sure to understand what it is that you missed. And come by my office or check with me during lab if you have any questions about any of those problems. What I want to do today is talk more about electric potential, which is the subject of chapter 24. Remember, this is not the same thing as electric potential energy, but in lab last week, and that was lecture topics that were covered in lab, so if you were just fell asleep because it was a lab lecture, I did post. Mark was nice enough to record my Friday session, and so you can take a look through that and make sure that you do understand the basic principles of voltage. I'm not going to go all the way back to the beginning on that. I'm going to assume that you understood the stuff that we were covering in the intro lecture last Thursday or Friday. Well, one thing that we did discover is that if we have a mass and we raise it to a certain distance, we have a change in gravitational potential energy. Whereas if we lift a charge against an electric field, we have a change in electric potential energy. So here the potential energy change would be equal to force, QE times distance, delta Y. And in this case, it would be mg times delta y, would be your delta U. So if Q is replaced by m and E is replaced by G, we have very similar relationships, and we have what's called the electric potential V. This is actually a delta V. This is the change in electric potential. Which we defined last time to be minus E dot delta Y, where this is a dot product indicating that if you go completely against the electric field, then your delta Y in this direction has an angle of 180 degrees with E, and that corresponds to a boost in electric potential. Now, if you go the other way, you go with the flow, it's like going downstream, that corresponds to a drop in electric potential. Electric field is measured in units of volts per meter times meter, so that gives you volts. But that's also equal to a joule per coulomb. Because we see here that delta U is equal to Q times delta V. And so if we move a charge through a voltage, then that charge experiences a change in potential energy. So that's the key thing that connects volts with potential energy. And this is the key thing that connects volts with electric field. So all of those different connections are going to be used. And so they should be real clear in your mind how they work. Are there any questions about any of those introductory ideas? Did we go with that? Okay. So let's go to this picture here. Let's say that we've got a voltage here, VA, is equal to 1,000 volts. And let's say that this electric field is constant in this region of space and is equal to 100 volts per meter. And let's say that we move from A to B, and this distance, delta x, is equal to 20 meters. What I'd like you to do real quickly here is find VB. What is the voltage at point B? And what's the difference in voltage? from what we've already talked about, should be able to do this. How many are done? Nobody's done? Still working on it? It's a very quick calculation if you know what the relationships represent. Very short one-step problem. You done?
Is it 100 times 20, which would be 2,000?
Is that what?
2,000 volts.
Which and
The change in volts.
so which one?
The first one?
Okay, delta V, good. So that would be, so we go back to our original expression. That would be delta V is equal to minus E dot delta X. In this case, we're calling the displacement delta X. And so this is going to be minus E times delta X times the cosine of 0 degrees. Because we're going with the electric field. We're going down in electric potential. So what are we going to get for this end? What was your answer?
2,000?
Is that plus or minus?
Negative 2,000.
Negative, good. So that would be minus 2,000 volts. This is going to be 100 volts per meter times 20 meters. So it gives you minus 2,000 volts per delta V. So therefore, what's VB?
Negative 1,000.
Good. Negative 1,000. VA was 1,000. And then we had a change in voltage of negative 2,000. So VB is minus 1,000 volts. Does everybody see how that works? Anybody have a question about it? That's a very simple calculation that it's not simple if you don't know what the relationships represent. That's one of the simplest calculations you can do. But as is true of so many things in physics, you have to see how it relates. And that's where the level of abstraction comes in, is understanding the relationship to the equations and why it makes sense that it would be that way. So if we're going this way, from negative to positive, what would delta V be? Positive 2,000, good. And that would make sense because we'd be going from minus 1,000 to plus 1,000, so that would be an increase of 2,000. So that would make sense either way. Okay, so that is a basic idea if the electric field is constant. So we go then from high voltage to low voltage with a positive charge. Now, if we have a negative charge, then it's the reverse, right? But you can always ground yourself to reality by realizing that a constant electric field starts on positive charges, and a negative electric field terminates. The negative charges are where the electric field would terminate. And so that means that a positive charge is going to want to go that way, but that's a drop in potential energy and a drop in voltage. Whereas a negative charge going this way, delta U is equal to minus Q delta V, right? Okay, so that means that a negative charge, like an electron, would experience an increase in potential energy because you'd be pulling it away from negative and toward positive. And so if delta V were negative, then the Q is also negative, so that gives us a delta U that's positive. So they've done a lot of studies with computing things with negative quantities in them. And they found that it takes about twice as long, and there's a lot more errors involved when the mind tries to compute negative quantities. And so then you start thinking, well, I can make a mistake here because delta V is negative, but because it's a negative charge, negative times negative is positive. You can get it that way from the pure math. But there's a couple of chances to make a minus sign in. Whereas if you just draw your little pluses in here and your minuses by knowing what is causing the electric field, then you can go back to a physical reality. You can see what's really happening in terms of pushes and pulls. And so that, I think, is a good thing to supplement the math, is to make sure that you have a good physical model in your mind of what should be happening. All right, so next, what I'd like to do, and there's all kinds of really fun applications of this stuff, but the next thing that I'd like to do is look at this relationship a little more carefully between work and changes in energy. So in this problem, let's say that we have a charge, Q, that is moving through this distance of 20 meters. And Q, let's say here, is equal to, let's make it 10 to the minus 2 coulombs. And let's say that this is a mass, M, that's equal to 1 kilogram. So let's, if it starts from rest here, and the electric field is still the same as it was before, so I haven't changed anything about the problem, except that I put a charge there that has this amount of coulombs on it, and it's 1 kilogram. The electric field is still 100 volts per meter. Remember, that's the same thing as Newton per coulomb from before. Just a different way of writing the same thing through that 20-meter distance. And let's say it starts from rest. Let's find the final velocity when it gets to here. And so that we don't confuse the voltages with the velocities, I'll put little feet on the voltages here. That can be unfortunate. We start getting that in there. Okay, so if we want the final velocity after it's been accelerated, we've got two different ways that we learned how to do this before in Physics 2.8a. Because it's a constant acceleration kinematics equation, we could first find the acceleration and then use the kinematics relationships to solve. And that's what you did on the last midterm when we had a problem like that. But there's an energy approach too, and sometimes the energy approach works easier and better. Particularly, let's say you didn't even know what the electric field was. Maybe you just knew the voltage. Maybe you just measured the voltage difference. Then you wouldn't even need to know what the electric field was to do this problem if you just use energy. So you could say that the loss in potential energy, that'd be Q delta V, is equal to gain in kinetic energy, 1/2 mv squared. Loss in potential equals gain in kinetic. And so instead of this being like an mgd, that's what we'd had before, an mgy, and then it would fall through a distance y type of thing, set that equal to 1/2 mv squared. Here we're just saying that the change in energy, Q delta V, this is the charge that moves through this voltage difference. This is the voltage difference. I get a voltmeter onto there, positive and negative, it's going to measure minus 2,000. Okay, and I know what the charge is, so then I can just say Q delta V equals 1/2 mv squared. That'll give me V here, this B and A, so this is B. It's okay to call that B fine, well it's not. Okay, so that's going to be the square root of 2Q delta V over M. Okay, and so I tried to make the numbers come out easy so I don't need my calculator. Be the square root of 2 times 10 to the minus 2 coulombs. And then delta V was 2 times 10 to the 3 volts divided by 1 kilogram. Okay, so then this is going to be 10 for, this is going to be 2, and then the square root of 4 times 10, square root of 40. It's what?
2 root 10. What you wanted to?
2, I just wanted to know.
6.
6.3 meters per second for V fine. Okay, so we could have done it with acceleration and with kinematics equations, but we could also do it with energy a little cleaner, a little faster, just one step. If you have to use kinematics and acceleration, first you have to calculate the acceleration, then you have to find the right kinematics equation that gives you what you want in terms of the final velocity. And so a lot of times the energy method is better. And the energy method works even if the electric field changes. So that's a really big plus, is that if the electric field changes over this distance, you can still use this energy method. And so that's the biggest advantage of all, of using the energy approach, is that there's only a very few kinds of situations where the electric field is constant. And in the rest of the situations, the electric field will vary. Any questions about that? So can you see that all we're really doing here is we found a new kind of energy, but then we're doing the same thing that we did in 288. So this is just applying the principles of electricity to the 288 stuff that we already know how to do. And if you think about it that way, it's not always that bad. You know, as long as you remember the stuff from 288. The next thing, we will get to lightning because I just love that subject, but not today. Today I want to just introduce a few more of the basic ways of working with electric potential. And so one of those is to look at the electric potential for a point charge. Now we already did this in lab, but we're going to look at this in a little more detail here. We saw before that the electric field is related to the voltage. And so there's a relationship between them. The electric field for a point charge is kq over r squared. It turns out that the expression for the voltage at a particular point, let's say we're here, this distance is r, then the electric field would be, that point would be kq over r squared. But could we also think about a voltage at that point? Well, the way to do that is to think in terms of, we said before in lab that the average electric field was equal to minus delta V delta x, assuming that the electric field is in the same direction as the delta x is in the same direction as the electric field. That's just a restatement of delta V equals minus E dot delta x. And if E and delta x are in the same direction, then we just bring that, assume here that the cosine of 0 degrees is equal to 1, so that the angle theta is 0 between them. Remember, dot product is E times delta x times the cosine of theta. That's what our definition for the dot product is. And so that's what we're doing here, E delta x cosine 0. So if that's the case, then you just bring the delta x over to this side and it looks like this. Then you can take the limit as delta x goes to 0, and this average electric field becomes an instantaneous electric field. And we get that this is equal to dE dx, or dV dx, with a minus sign on it. So in the limit then, as delta x goes to 0, E instantaneous, not average anymore, got rid of that average thing, equal to minus the partial of the voltage V with respect to x. Okay, and so this is if E is just a function of x. But in this problem, it's a little different. E is a function of r. And so how do we do that? Well, it's pretty straightforward. If E is just a function of r, then all we have to do here is replace the x by r. So this gives us E of r equals minus dV dr. So that means that we can get the electric field by taking the slope of the voltage curve, the negative of that slope. Now remember that voltage is a scalar, but when we drew all of our different little voltage equipotential lines in class, remember all that stuff that we did? Although these are scalar quantities, we had a change in voltage, and so this gave rise to the steepness of the curve. So we can think of this as being like a hill, and this as being like a valley. And these are being like topography lines on a map, except these are equivoltage lines instead of equi-elevation lines like you would have on a topography map. So E then is just the negative of the slope of V of R curve. And so if we know that the electric field E is equal to KQ over R squared, then we should be able to figure out V by just thinking, well, what function can I multiply, or can I take the derivative of that'll give me that? And so let me think. Well, I could guess the wrong answer, but I'm going to guess the right answer. Let's try V's KQ over R. Let's just see if that works. And then if we plug that in, so that means that V versus R is going to be a 1 over R curve. Do we all know how to draw that? Here's V versus R. This is 1 over R. So that gives us, so if we go twice as far away, the voltage, it's not cut by a factor of 4 like it would be with an inverse square, cut by a factor of 2. So this is proportional to 1 over R. So if we take the slope of that and hit it with a negative sign, what we're going to get here is minus, and then minus 1 times KQ times R to the minus 2. Minus 1, and then this is to the R to the minus 1 power, which is just plus KQ over R squared. So that checks out. We already showed that the electric field was KQ over R squared using Gauss's law. And so what we found here is that the voltage KQ over R is consistent with this relationship that was derived by Gauss's law. So that proves it. There's another way of proving it that's done in your book, where they integrate from infinity to R, the electric field. And I'm skipping that way of doing it for the moment, because I think that's unnecessarily complicated. that's good enough. If we can see what the answer should be, and we can plug it in, and we can get the left-hand side to equal the right-hand side, good enough for me. On an algebra class, maybe, you have x squared minus 1 equals 0, and you just start plugging in values for x, they probably mark it wrong. But these problems are a little more challenging, so if you can guess the right answer, plug it in and show that it's correct, that's considered to be okay. Especially in differential equations, you do that a ton in differential equations. So that's all we did here. We guessed this solution, and we showed that it gives us the right answer. And so your math teacher would probably be tearing his hair out. But for physicists, this is just fine.
Sorry, well, why did we choose KQ over R to plug in for V?
Because we wanted to take the derivative of it and get the right answer for the electric field, which we already know is KQ over R squared. Any other questions? Okay, now if you like the more rigorous definition, you can look at what they do in the book. V is equal to the integral from infinity, minus the integral from infinity to R of E dot dr. And you'll get the same answer. But you've got like 3 or 4 minus signs that you've got to get right, and it's just, I don't think it's as clear what's going on. Really easy to make a mistake. But this is simple. If you just understand that this is the, and so if we go back to this curve, we take the slope at a certain point, then that slope is the minus of the electric field. So if the slope of the electric field at that, or the slope of the curve at that point is negative, means the electric field is positive. The electric field here we see is positive. It's pointing straight away from R. And so if we're negative, then it would be pointing this way. But it's not. It's pointing that way. And so that's consistent then with the negative of this slope being equal to the electric field. So if we plot this up then we can have constant voltage lines that are spherical shells that surround the charge. And those aren't going to be equally spaced because you get in here closer and a little tiny change in R is going to give rise to a huge change in V because you're approaching a vertical asymptote. Right? This is basically a mountaintop that's infinitely tall. Okay, so this is like the topography for a mountain. If you saw something like this on a topography map, and you saw a lot of really tightly spaced lines in there, and you go, oh, it's getting really steep toward the top. But here, the lines become infinitely closely spaced, indicating that you have an infinitely tall mountain. And is that the way it really works? Well, probably not. I don't think there's really any true infinities in this because it's not completely a point charge. So you eventually get down to the size of an atom, and then at that point you're not really too worried about this anymore. But from an idealized mathematical perspective, that would have an infinite slope. But as you start to move out, these lines of constant voltage become more and more widely spaced. And so what does that indicate in terms of the electric field? Well, you can see that the electric field then is drawn as being perpendicular at every point to those equipotential lines. Just like what we did in lab. So that was a great lab for what we're looking at now. And we can really see why that works the way that it does. And so we say that the electric field then is the gradient of the voltage curve. You may have heard about that in your math class. That along the path of steepest descent. You ever heard that? So this is real. This is what that really means for a physical problem. All right, so let's look at it for a dipole. Positive, negative charge. Okay, so if we want to plot the voltage for each one, here, this is going to come in like -1 over R. So, this is going to look like this. But it also goes out this way too because it's spherically symmetric. So it's one, this is V versus R. That's for the positive charge. And then it would also come out this way. It would come out from behind too. But we're just looking at a cross section over here. And so then for this one, it's going to look like this. This looks like V is proportional to -1 over R. So that's like, if this is y equals 1 over x, then this is minus 1 over x. That's going to look like that. So that's your -1 over R. Now, the voltage is just add in the region where they connect together. And so if we add these two together, what we're going to get is something that looks like this. And so what does this tell us about the voltage at the midpoint?
0.
Okay. The voltage at the midpoint is 0. You can see that right from here. Okay, and so how do we do that mathematically? Well, if we want the voltage at this point, we'd say V total is equal to KQ over R. This is particle 1, Q1, plus KQ2 over R. This is Q2, but it's negative if the magnitude of Q1 equals the magnitude of Q2 for a dipole. Then this is just going to be KQ over R minus KQ over R equals 0. So the voltage is 0 there. Now, if something has a 0 volts, then how much work would it take to bring something in from infinity? Let's say another charge here, and I want to bring it in from a really far distance away. And put it right here. How much work is that going to take? 0. That's right, because there's no change in voltage. Remember that the change in energy, delta U, which is also equal to the work done, is going to equal, in this case, Q times delta V. Okay, so this is V initial. But we're out here at infinity, so that's 0. This is V final. Remember, it's a difference in voltage. That's also 0. We just showed that that's true there. And so that means that the difference in voltage is 0. And yet, if I put a charge there, is it in equilibrium?
No.
It's not. So what we could say then is that I did no work to bring it to that point, but once I let it go, it's going to start to move. Now, can I say that if the curvature here is negative and the curvature here is positive, that the slope is 0 at that point?
Yes.
You might think so, but what is the slope equal to in this case? Is the electric field the slope? Yes. The electric field is the slope of our voltage versus our current. And is the electric field 0? No. We learned that before. We've got electric field E1 from particle 1. And we've got for particle 2, electric field E2. Those two add, so we get an E total. That's equal to 2kq divided by, and then if we call this distance 2L, the total distance between them, then this just would be 2kq over L squared. Okay, so that means that at a point of inflection, where you have the curvature changing, you don't necessarily have 0 slope. You can have this thing change from a positive curvature to a negative curvature, but the slope is non-zero at that point. You know, it may look like it should, that this should make a transition to there that would give you 0 slope there. But in this case, that's not what's happening. That's not what's happening at all. But you do have a minimum slope at that point. So the slope isn't 0, but it's a minimum value. What does that mean? It means that if I moved in closer, say in this direction, the total electric field would be bigger. If I moved in closer in this direction, the total electric field would be bigger. Because here I would either be, say here, or I'd be here. And in either case, the electric field is bigger than it is there. Because you're closer to one, and that more than makes up for the fact that you're farther away from the other. If you're twice as close to this one, then it's 4 times the electric field for this one, but only 1/4 for that one, so you got 4 1/4 instead of 2 times that value. And so it's double by bringing it in twice as close, almost. And so these slopes are bigger then, but at that midpoint between them, the slope is a minimum, but not equal to 0. So that means that this is a point at which you could put something, but it's unstable. It would tend to move. Any questions about that? You know, what would happen if I started, instead of adding up the electric potentials for a dipole, what if I just took 2 charges that were positive? And I want to know what the voltage was between. Let's say this distance is L and that distance is L. B at the center. This is the electric potential difference. What would it be then? Well, it would definitely add the 2 together. So this would be kq over L plus kq over L. So that would be 2 kq over L. But what's the electric field? The electric field is 0. So here we have a non-zero voltage, but a 0 electric field. Here we have a 0 voltage, but a non-zero electric field. So how does this one look? Well, this one, you've got your 1 over r curves for each one. Look like that. So when you add them up in the center, you get something that looks like this. And then it goes off on the sides. So this is V proportional 1 over r. B proportional to 1 over r. Remember, this is spherical coordinates r, so r goes away in all directions. This is a negative r, because r is 0 at the center of the sphere. But then in the middle, This is going to be non-zero here for the voltage. So the voltage here is 2kq over L. That's what it is there. But the slope is 0 because the electric field is the slope of that curve. Okay, and so you can pull that back out of the math just by doing the correct plot of the voltage versus R, and then looking at the slope of that curve to see how the electric field is related to the electric potential. Okay, so now, if I want to bring a particle in from infinity, Q, but now I want to put it here instead, am I doing work? Yeah. Okay, so the work that I would do then, in bringing it in, so I'm bringing this in all the way to here now. So the work then equal to Q times 2k little q over L. Yeah. And so, but here, if I bring it into here, then the work is equal to Q times 0. And so why physically do I have to do work to push this positive charge to here, but not doing any work to push it to there? Why physically? What do I have? You can imagine that the charges, when you push against the charges, it's like loading energy into a spring. You want to think of it that way. So as you bring this thing in, can you see that you're having to push against both of those charges to bring it in? You've got to push against both of them. And so they're both pushing back on you, and so that means that you have to exert a force through a distance to get it to there. But here, you've got to pull back on it to keep it from going to this one, but you've got to push on it, push against it, to get it closer to that one. And so those two effects just cancel. The amount that you're being pulled toward the negative and the amount that you have to push toward the positive are equal. And so therefore, you're doing no work. That's the physical interpretation of this. If you didn't get that, you might want to double check it when I put it up on the video. And just think about it, because that's important. It's an important concept here. And sometimes these things, they take a little bit of thinking. So if you've got the video, you can look at it, you can stop it. You know, does that make any sense? And then 10 minutes later, you can go back, replay it, and then you can move on. But are there any questions right now? All right, next, what I'd like to do is figure out, and here we're trying to connect together the ideas of work and energy with these problems. So in the next example, let's try to find out how much work it would take to bring three equal charges together into an equilateral triangle. We got Q1, here, Q1, Q2, Q3. So they're all at a distance d apart from each other. And for simplicity here, let's say that the magnitude of Q1, they're all positive, let's say. Q1 equals Q2 equals Q3. You can set that as 10 to the minus 5 coulombs, just for fun. And then and d, let's say, is 1 meter. So I could also call this just some generic Q if I want. And so let's ask then, well, how much work is it going to take to bring these together? From a long distance away. Okay, so when we say here V is equal to KQ over R, what we really mean is that this is the voltage difference between R and infinity. So if I have a positive charge here, let's say this is 1 meter away. This is Q equals 10 to the minus 5 coulombs. Then, if I take a voltmeter here, and there are problems with doing this in a space because you don't have a conducting medium. But when we did this in lab, we had conducting paper that would allow our voltmeter to work. So this kind of a voltmeter wouldn't work doing this. But the principle is still the same. So if you take the positive end of the voltmeter and connect it to there, and you take the negative end and you put it here at R equals infinity, which we could say is the same thing as ground, then the difference between them is KQ over R. So this is really V R minus V infinity. That's the voltage increase in bringing an object from 0 volts to this value. And so in this case, if Q is 10 to the minus 5 coulombs and R is 1 meter, then this would be 9 times 10 to the 9 Newton meters squared per coulomb squared times 10 to the minus 5 coulombs divided by 1 meter. Now would give us 9 times 10 to the 4, or 90,000 volts. So that's what we read here is 90,000. If I measure, because that's the voltage difference between 0 volts and the volts that I have at this point. So even though it looks like it's just a state of voltage here, what's implied is that this is a voltage difference whenever we see this kind of an expression. And so, given that that's the case, let's see if we can figure out how to do the work for this problem. How should we do this? Well, what's tempting is to figure out all of the potential energies between all three of these things. But the problem with doing that is if I figure out the potential energy between A and B, then I figure out the potential energy between B and A, I'm counting too many times. And that's an easy mistake to make. So instead, my strategy is going to be to bring them in one at a time. Then we'll have a work 1, a work 2, and a work 3. This is the work to bring in charge 1. But there's nothing else there. So what is that work equal to? 0. So this is Q1. I'm going to bring it into here, but I don't have to push against anything. So I get the first one for free. Work 2, that's the work done to bring in Q2 subject to the influence of Q1. So over here at minus infinity is my Q2. So now I'm going to bring it in. Doesn't matter what path. And then we end up here. This is what we call a conservative force if it's path independent. The only way that it can be path independent, though, is if there's no friction or anything else acting. But that's the case in this problem. We're assuming none of those things are happening. So we're bringing it into this distance d away. And so W2 is just equal to Q2 times delta V1. But that's just Q times KQ over D. This is voltage 1. Okay, so that's the voltage that's produced by particle 1 at this location, away. Then I'm bringing this in from infinity to that point. And so the difference in voltage is KQ over D times Q. That gives us KQ squared over D. Or this is Q1 and this is Q2. So that's our more general expression. But since they're equal in this case, we can write it as KQ squared over D. This also gives us a good expression for change in potential energy. Delta U then is Q1 times KQ2 over R in general, or KQ1 Q2 over R. So this is a general expression then for a change in potential energy. So that's the potential energy of two charges that are at a certain distance away. We can look at that as being kind of analogous to what we had before with gravitational masses. You had a mass m1 and a mass m2. Then the potential energy between them, U, is equal to minus g m1 m2 over r. That's what we got. And we used that for spherical planet problems in 208A. The reason for the minus sign there is that gravity forces are always attractive. And so here, if we have the same charge, this is going to be an increase in potential energy. But if they were opposite charges, it would be a decrease. But we have the same relationship if you make the replacement that G goes to K and M goes to Q. We have essentially the same relationship for the change in potential energy. So that's what my W2 is here. That's Q2 times delta V1. Then W3, that's the work done to bring in Q3 against Q1 and Q2. Okay, and so way over here, my Q3, bring that in from this infinity away. Path independent, bring it into that location. And so now, what I have to do is write this as Q3 times delta V1 plus delta V2. Okay, because we've got KQ1 over D plus, and then this is not directional. Remember, it's a scalar quantity. So I don't want to ever see anybody taking components of a voltage vector. No matter how many times I say that, I'm going to get that on the next exam. But I hope it's not you. So that's going to look like that. So we're just adding them together. So how would that change if I had the two charges like this and the third one here, and this was D? It wouldn't change at all. Doesn't matter how far, how close they are to each other, because voltage is not a vector. And everybody wants to draw it as a vector because that's what we did with electric fields. Remember, voltage is a scalar. So this is the same voltage as this is. That's the same voltage as this is. As long as they're the same charges, in each case, all of those have the same voltage at that point. Because you don't have any components to worry about. It's just a scalar quantity. All right, so this is going to be Q3 times, well, okay, so at this point, Q3 and Q1 and Q2 are the same. So this is Q3 times 2K cubed over D. So that gives us 2K cubed over D. And that's my W3. So this is my W3 calculation. This is my W2 calculation. And my W1 calculation, I got the first one for free. So remember that work is a scalar quantity. We add them together, like numbers, no components. What turns it into a vector is when you look at the slope of the voltage curve. Then that's a vector, but not the voltage itself. That's a scalar. So W total is going to be K Q over D plus 2K Q over D. That gives us 3K squared. 3K Q squared over D. Did I get that here? No. Now it's a squared, that's a squared, because you have Q times Q. Okay, so it's 3K Q squared over D. And so the total work then is going to be 3 times 9 times 10 to the 9 Newton meter squared per coulomb squared times 10 to the minus 5 coulombs squared over 1 meter. So that gives us 27 times 10 to the minus 1, or 2.7 what? Newton meter, or joules. Joules. Now, what if I let go of them? Now, if I let go of all three of them at the same time, I'm holding them in place so they don't repel from each other. Well, what if I let go of them? What is the resultant motion going to be? They'll try to go back to infinity along paths that are going to be at a 120-degree angle to each other. You have zero initial momentum, and so you have zero final momentum. This will be this one, and you'll have this one and that one. So the system will have zero total momentum, but the energy, because of the symmetry of all three of these have the same mass, the total energy would be 3 times 1/2 mv squared. So work total could then be turned into kinetic energy along each one of those paths. And then you could find the velocity of each one of those, and it'd be equal if you had equal masses and equal charges to start out with. This one would take off that way, this one would take off that way, this one would take off that way. And that would be it. So you can figure out the velocities of those things if you let them go. I'm not going to do that here, but you could do that. Are there any questions about that? Yeah.
Why is the work to bring in the first charge 0?
Because you didn't have to push against anything. I brought them in one at a time. So there was nothing else there. So I moved it against a zero electric field.
Oh.
Got the first one for free. And then the second one, I bring it in against Q1. And the third one, I have to bring in against Q1 and Q2. And that way you don't count twice. Because it's easy to go, well, this potential energy, Q2, Q3 over R. And then, well, there's this one too, K, Q3, Q2 over R. You know? And then you've counted too many times. You have a factor of 2 error. Question?
Mathematically, is there another way, because your strategy is to do one at a time, is there mathematically any other approach?
Well, yeah, you could just keep track of, you know, if you have the same indices, then it doesn't matter which way you switch them because it's commutative. You know, Q1 times Q2 and Q2 times Q1 are the same. So you could bring in Q3 first and then Q2 or Q1, or you could bring them all in at the same time. Doesn't matter.
Gotcha.
Any other questions? Right. So with those ideas in mind, let's look at one other kind of work energy problem. Let's say that we have a single charge, big Q, and a smaller charge, little q, that are initially separated by a distance d equals 1 meter and held firmly in place. Let's say big Q is 2 times 10 to the minus 5 coulombs, and little q is just 10 to the minus 5. So let's let this thing go, and let's find the final velocity if we let it go to infinity. There are a couple of ways I could do this problem. So this one we hold solid. So this one is not going anywhere. But we let this one go. Now if we did hold this one solid, then this one could repel, and that's going to affect our result in a way that I don't want to deal with right now. But if I let this thing go, then by the time that we get to here, let's say we're at a distance d equals 2 meters, then I'm going to have some kinetic energy, but I'm also still going to have some potential energy. So we'll start out letting this thing go to 2 meters, and then we'll let it go to infinity. So we start out here at 1 meter, we let it go, and then we want to know V final when it's at 2 meters away. You go, well, we could say, well, it's EQ times D. Can we do that? No. Why not? The E is changing. Remember, E, the voltage V equals minus E dot delta X. But if and only if E is a constant. Not the case here. The electric field is varying as an inverse square law. So that means that can't do it that way. Does everybody see why we can't do it that way? Even though we've done a lot of problems with constant electric fields, that's just to break us in to some more advanced, sophisticated kinds of problems that are the majority of problems where the electric field isn't constant. Right, so we'll use conservation of energy for this. You can say that, well, remember when we did this for masses, we had 1/2 mv initial squared plus, this was minus g m1 m over r1 equals 1/2 mv final squared minus g m1 m over r2. So these were our potential energy terms. These were our kinetic energy terms. And we solved some problems doing that. Kinetic energy initial plus potential energy initial plus kinetic energy final plus potential energy final. So what do we replace that with? Well, when we do potential energy, that's U for point charges. That's going to be KQ1, Q2 over D. That's what we showed before in that earlier example. This is Q times the delta V for the other point charge. Okay. And so that's just K, Q1, Q2 over D. So be careful now, because we've got a lot of relationships here that look similar. E looks like KQ over R squared. F is QE, so that's K little q big Q over R squared. We have electric potential, which is KQ over R. And we have electric potential energy, which is KQ times big Q over R. Two of these are vectors, and two of them are scalars, and they look kind of similar. And they're easy to mix up. But even in a Physics 205B class, you would be expected to know the difference between them. And so this is important that you are clear enough about this so that you're not going to make these kind of mistakes on an exam. But this is what your potential energy is going to look like. This is your voltage, but difference in potential energy is Q times voltage. So that's why this follows directly from that. And F equals QE, this follows directly from that. Okay, so just make sure that you drill that in, that that's all real clear to you. So what we're going to replace this with then is 1/2 mv initial squared plus KQ big Q over R1 equals 1/2 mv final squared plus KQ big Q over R2. Not over R squared, but over R. For over R squared, it would have the wrong units. So that's one way to remember. Here, this has units of newtons, but energy has units of newton meter. So the R in the numerator can cancel out the R in the denominator. That's not exactly, I mean, from a unit point of view, you can think of it that way. That's not the way to derive it, but that's the way you keep it straight in your head. Okay, so this is just conservation of energy for an electrical problem that looks just like our spherical mass problem if we make this substitution. So I don't know how many of you were able to get this right, but if you understand that principle, then this one should just naturally follow from it. As we're just making the substitution, Q goes to K, M goes to Q. All right, so let's solve this problem. We need to know what this mass is. Let's set this mass equal to 10 to the minus 2 kilograms. For fun. And so then here, we're going to have 0 initial kinetic, but we do have potential. and we're going to have final kinetic and final potential. So that means that 1/2 mv final squared is going to equal k little q big Q times 1 over R1 minus 1 over R2. Just doing the math. This is R1. I'm bringing R2 over to this side. Then I can multiply both sides by 2, divide both sides through by m, and take the square root of both sides. That gives me V final. Okay, so that's just math. But be careful, because it's easy to make algebra errors, especially if you haven't done this kind of thing. So V final then here would be equal to square root of 2k, 9 times 10 to the 9, Newton meters squared per Coulomb squared, times little q, 10 to the minus 5 coulombs, times big Q, 2 times 10 to the minus 5 coulombs. All divided by m, which is 10 to the minus 2 kilograms. Okay, so this is going to give me 9 times 4 is 36, times 10 to the minus 1. But then we'll bring this up, and that'll be 10 to the 2. So that's square root of 36 times 10 to the 3. So that's the square root, that's 10 to the minus 1 and plus 2. That's 10 squared, right? Everybody with me there? Is that right? This is 10 to the plus 2. No, that's just 10. Okay? This is 10 to the minus 1. Then we bring a 10 to the 2 up to the top. That's a 10 to the plus 1. And so that's 360. What's the square root of 360? 360? Well, it's 6 times the square root of 10.
18.97.
Thank you. 18.97 meters per second. So that would be my V final. Does everybody see how we do that? Just using conservation of energy? Oh, that's 1/2. Whoops. Should be divided by 2 in here. That's a square root of 2. Okay, this is 1/2. I forgot to do that. This is 1 minus 1/2. This is 9 point. Isn't that this divided by 2? Divided by square root of 2.
13.42.
Okay, thank you. So this is just 1 minus 1. Okay, so if I wanted to rewrite this then, I could rewrite this as square root of 2k little q big Q over m times 2. Then the 2's would cancel. So that would give me square root of k little q big Q over m. Probably would have been easier to do that. Okay, so now, what can we say about the ratio of kinetic energy to potential energy here? Can we say anything about that? In the final situation, here it's all what? Potential at the beginning before we let it go. But then once we let it go, is all the potential gone? And we still have some, but we have some kinetic. So what's the ratio between them? Inverse of what? I I mean like 2 to 1, 1 to 1, 3 to 2, 4 to 3, what would it be? How are they divvied up? If I had a potential energy container and a kinetic energy container, and they're filled with water, how much water would be in each one? 1 to 1. How did you get that? That's right.
Well, I was just thinking, there's, you know, if you think about it like as, instead of all the numbers, just KE and PE, there's one
Yeah.
each.
So this is half of this, right? So that means half of the energy you wanted to put into kinetic, and you got half left. Good. Exactly right. So the ratio then of kinetic energy to potential energy at that point, when it's double the distance away, is 1 to 1. Half of the energy is turned into kinetic, half is left. But what if I let it go all the way to infinity?
It's all kinetic, so initially.
Then it's all kinetic. Let's rewrite our expression over here.